This is the lecture video for gravity and Newton's laws. Get out a new piece of paper. Remember, you can pause, rewind, watch again to get the notes that you need. This unit, we're going to learn about how the planets orbit the sun, also how moons and satellites orbit planets. So in order to do that, we have to understand Newton's law of universal gravitation. But while we're on that topic, I think it's important for us to also quickly look at Newton's laws of motion and then Newton's law of universal gravitation. The laws tell us basically how things move or how they sit still. Now, it's really important because these laid a foundation that enabled us to understand how cars work, how water flows, how tall buildings like skyscrapers, bridges, how those things don't fall down. So everything that is around us that moves or sits still, these laws help us understand that motion or lack of motion. Now, Newton has three laws of motion. The first is that an object at rest will remain at rest unless acted on by an unbalanced force. And an object in motion continues in motion with the same speed and the same direction unless acted upon. Now, let's just think about this in simple terms. Let's say you're in space. Here you are in space, billions of light years away from anything. So there's no gravity around you. You're in the vacuum of space, no air, no nothing. If you throw a ball, that ball, according to Newton's first law, is going to move at the same speed that you threw it in the same direction forever and ever. It'll never stop unless an external force is applied to it, right? What does that mean? Well, now let's think about, instead of in space, let's put you on Earth. Okay, you're on the Earth, you throw that ball. Why does that ball stop then if you're on Earth? Well, that's because on Earth, there is an atmosphere. There are gases in the air that are hitting the ball and slowing it down. Imagine throwing a ball underwater. Very similar. We can understand that because we see the water. People forget there's air all around us, gases all around us. Those slow the ball down when you throw it. That is an external force. Also, we have the gravity of the Earth pulling the ball down. So eventually, if you throw a ball on Earth, it won't go the same speed because it's losing speed to the air resistance, wind resistance, and eventually it's going to fall and hit the ground. Now, that ball, according to the first law, will not move unless an external force is applied to it. So it's not going to move there unless somebody kicks it or moves it or the wind blows it. There has to be an external force or else it'll stay still. Newton's second law says that acceleration is produced when a force acts on a mass. Objects with more mass require more force. This one's obvious. Now let's imagine that ball. It's not going to move, right, according to the first law, unless you kick it. You have to give it a mass. Now imagine that ball is now a huge boulder that weighs 2 tons. If you kick it, it probably won't move. But if you get somebody really big or you get a forklift to kick it, technically, move it, then it will move. So in order to get an object to accelerate, you have to put a force on it. Now the third law says that for every action that occurs, there is an equal and opposite reaction. Let's go back to space. Let's say you're in space again, and you're going to throw that ball. Well, we missed something when we threw that ball. If you're truly in space, and you're not stuck down on the ground, you're not using your muscles to push against your throw, when you throw that ball, and it goes that way, from that force, there is an equal and opposite reaction. When the ball goes this direction, your body will move in the opposite direction. So you and the ball will move away from each other in equal and opposite directions. That is why if you put a book on a table, the book does not fall through the table. The table is exerting an equal and opposite force that the book is pushing down on it. So now let's go on to Newton's law of universal gravitation. It says that every particle in the universe attracts every other particle. There's a force of attraction, gravity as you know it, that is in a straight line from the center of one object to the center of the other object. Now, the force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Sounds fancy, right? All that means is that the force of gravity gets stronger, directly proportional, if the masses are bigger. So if you have two really big things, they have more gravity pulling them together. Now, inversely proportional means that the amount of gravity, the force of gravity between two objects, it decreases as they get further apart. So let's kind of look at an example. You're going to do this in a lab after this assignment. If we look at the Earth and the Moon, Newton gave us his fancy law, an equation for the law of universal gravitation. And so if we know the mass of the Moon and the mass of the Earth and the distance between their centers, then we can figure out how much gravity or the force of gravity that is between them, that's pulling them together. One thing I want to mention is that you have to make sure you have the correct units to do these calculations. The masses have to be in kilograms. The distance, the R, has to be in meters. And G, this part G here, is actually a constant, which equals to this. If we do equations like this, I'll always give you everything with the proper units. But, as you go through high school and if you go to college, you're going to have to learn how to transfer from one unit to another unit. We'll work on that later on this year. So if we know that the Earth weighs this much, the Moon weighs this much, and there's this much distance between them, then we can do the calculation. I did it already to save time. That the force of gravity, there is 1.99 times 10 to the 20th newtons of gravity between the Earth and the Moon. Now, as you'll see, that changes a little bit because the Moon's orbit is not a perfect circle, so the distance changes a little bit from time to time. But those are Newton's laws.